In this video, I'm going to briefly talk about the Hausdorffness of the topological group. Okay, so by doing that, usually the idea is that even though we don't assume the topological group to be Hausdorff, but most of the time we do because we can always quotient out the non-Hausdorffness of the space to make it Hausdorff. Okay, so that's the entire idea. So to do that, I need to introduce a little bit on the quotient topology and the quotient space. All right, so let's just recall how you put a quotient topology. So let's let H to be a subgroup of a group G, a topological group G. So the left coset we saw last time, basically all the left cosets. And you have a canonical quotient map. You map from G to the cosets. Basically, you take an element X, map it to the corresponding coset. And G has a topology. G is a topological group, so it has a topology. So you want to put some topology on the cosets. Basically, you just want to make this quotient map to be continuous. Okay, so that's how you put the quotient topology. You put the smallest topology so that this quotient map is continuous. That's the quotient topology. And well, this looks really fancy, but in reality, it's really simple to check. So for a set in your the set of quotient to be open, as if and only if the inverse image under this quotient map Q is open in your original topological group G. Okay, so this is how you check a set is open. So the first lemma I want to talk about is that this Q is always an open map. In other words, it maps open set to open. And that's really simple to see. So let's just quick proof. So if you have V that's open, as let's say contained inside G is open, and you want to know whether Q of V, its image is open, so you consider its pre-image of this Q of V. Okay, so let's think about what that is. So that is essentially all the X in G where there exists some V in V so that your image under Q is equals to this coset of this V. So XH is equals to this VH. And if you recall from your group theory, so XH and VH are the same if and only if X is inside this VH. Okay, so that's the same of saying your X is inside VH for some V inside V. And another way of looking at it is that, well, X is just equals to V dot something in H. So this is essentially just V dot H, okay? So here V is an open set and you dot an H and you can convince yourself this is essentially just all the right translation of V by things in H, okay? So you take the union of all the Y in H, you right translate this open set. Each right translation is open we saw last time. So you take the union, this is open. Okay, so you have that is open, so Q of V is open, so Q is an open map. Okay. All right, so I want to briefly talk about, now we want to look at this quotient of G mod H and want to see whether you can have some you can make it a topological group. Okay. So here is the proposition. So H is a subgroup of a topological group G. And then I have the following. So first of all, if you have H is closed, then when you quotient out, you will have something that's Hausdorff. Okay, so when you mod out this closed subgroup, then you have something that's Hausdorff. Okay, so that's going to be important as we construct a quotient space that's Hausdorff from a potentially non-Hausdorff topological group. And second, we want to say when is if G is a locally compact, basically means every open neighborhood you can find some compact neighborhood. Okay, so then this quotient is also locally compact. Okay, I'll just use LC to say locally compact. And finally, if you have a normal subgroup, okay, so if H is not normal, of course, your quotient space is not a group even. But if H is normal, so use this notation, is a normal subgroup of G, then you can conclude that your quotient space, you know it's a group, is actually a topological group. Okay, so it's a topological group. Okay. So here is the proof. Well, for the first one, okay, so let's basically to show its Hausdorff, I need to show that if I have two xy, so any x and y, so that xh is not equals to yh, I need to find some set that separate them, okay? So one thing we know when xh is not equals to yh is that, first of all, I can consider xh y inverse, okay? So first of all, H is closed. So when I translate the closed set, well, it's clearly also closed. And then I right translate by Y inverse is also closed. And because XH is not equals to YH, then I know that identity cannot be in there. Okay, so you have something like XH Y inverse, and you have identity here. All right, because identity is away from that, you can, well, you have something this is closed. So its complement is open, identity is in there, so you can find a open neighborhood. Okay, so there exists open neighborhood E inside U, inside your topology. Okay, so that let's say U intersect this X H Y inverse is going to be equals to empty. And once we have this open neighborhood, I can basically make something that's even better. I can, with a lot of generality, I can find a even sub-neighborhood of this U. So maybe here's U, I can find something that's even smaller so that it is symmetric and is the U dot itself is still inside, is still destroyed from X, H, Y inverse. Okay, so with a lot of generality, we may just assume that U is symmetric and U dot U is also disjoint from the XHY inverse. Okay, that's also equals to empty. Okay, so what does that mean? Well, I want to claim the following fact. I want to say that, okay, so now I want to make the claim that this U basically going to help me separate the XH and YH. In other words, I want to claim that UX, if you consider UX their coset, and you intersect the UY, okay, their coset, they're going to be equals to empty. Okay, so basically that gives me this separation of these two cosets. Okay, so well, how do we show that? Well, let's consider for every U inside U and every, let's say, V inside U again. Okay, I want to show that this UXH intersect VYH, that's going to be empty, okay? And to show that is empty, that's essentially just, basically I need to show that this is equivalent of saying this UXH times the VY inverse, so I have Y inverse, U inverse, that's going to be, doesn't contain the identity, okay? So identity is not in there, okay? So, well, how do I show identity is not in there? Well, basically that's equivalent of saying for every H inside H, this UX, if I replace the middle thing H, and Y inverse U inverse, that's not going to be equals to identity. Okay, they're the same. Well, what happens if they equals to the identity? Okay, so here's a V here. Well, if they're equals to the identity, so if otherwise, then what I have, I can move the U and V to the other side. I have X, H, Y inverse. That's going to be equals to, on the left-hand side, I have a multiplier U inverse, and the right-hand side, a multiplier V. So on the left-hand side, you have something coming from X, H, Y inverse. And on the right-hand side, you have something coming from U inverse dot U, which is just U dot U because U is symmetric. Okay. But we know these two sets are disjoint. Okay, so this is a contradiction. Okay, so by our choice of the U dot U has to be disjoint from the XHY inverse. Okay, so this proves this claim. And because of that, then we basically know that if I take Q of this UX, we know Q is an open map, so UX is open, so the image is also open. And this Q of UY, they're both open, and their neighborhood, they're both open neighborhood of this QX and QY respectively, and they certainly destroy from each other, so I have this as Hausdorff. Okay, the next thing is fairly simple. So if I have G is locally compact, so G is locally compact, then because my Q is continuous and open, so I have Q of U is open for every U is open, and the Q of K is compact for every K compact. Okay, so clearly its image is going to be locally compact. Okay, this is kind of trivial. So lastly, I need to show the following. If I have a normal subgroup, then I have a topological group. Okay, so let me first of all check this multiplication map is continuous. So to show that, if I take any element x, y, h inside some open set, so U is open inside this G mod H, this quotient group, then I basically need to find two neighborhoods in this quotient map. Okay, so the idea should be quite simple. Because my x, y, h, this coset is inside U, then x, y is certainly inside the Q inverse of U. Okay, the Q inverse of U is open. So this is open. So by the continuity of this multiplication in the group G, then there exists two open neighborhood of x and y that's called V and W. So x in V, y in W. They're open neighborhoods in G. So that this V dot W is going to be contained inside this Q inverse of U. Okay. Well, then you can convince yourself when you do the Q of them. So Q of V dot Q of W, that's going to be contained inside Q of Q inverse U. So that's going to be inside this U again. Okay. And clearly the Q of X is inside the Q of V. Q of Y is inside Q of W. So there you go. It's continuous. You can do the same for the inverse. Okay. It's basically the same thing. All right. So let's finish the proof that if you have a normal subgroup, you take their quotient group, that's going to be a topological group again. So now I want to show the following thing about, talk about the Hausdorffness of a topological group. So the idea is that if you're given a potentially non-Hausdorff topological group, then a lot of things are messed up with each other, okay? So your topology cannot differ your elements. So if you look at the element singleton 1, then a lot of things are messed up with this 1 by your topology. So you take the closure of the singleton set 1, you get a closed set. It turns out all those things that you cannot differ by your topology is going to give you a normal subgroup. Okay? Because you close it up, it's a closed subgroup. And because it's closed subgroup by the proposition which is proved, its quotient is going to be a Hausdorff space. Okay, and because you have a normal subgroup, so it's not only Hausdorff, and you actually get a topological group. Okay, it's a Hausdorff and a topological group. So the proof really just goes to, I need to prove the first part of this theorem, this corollary. Basically, I need to show the closure of the singleton is a normal subgroup. Well, first of all, from last time, we know the closure of a subgroup is again a subgroup. Okay, this is from the last video. Okay, so singleton in itself is a subgroup. You close it up, you get a subgroup as well. So H is certainly a subgroup. That's no question. Okay, is a subgroup is clearly closed. Okay, that's kind of trivial. Close it up. And now you want to show it's normal. Okay, so you only need to show it's normal. So when you quotient out, you actually get a group. Okay, so suppose it's not normal. Okay, so if H is not normal, then what can go wrong is that there exists some G inside G, so that your GH G inverse, okay, you conjugate it, that's not going to be equals to H. Okay, it's not even contained in H. Okay, so that's not equals to H. Okay. So, well, your H is closed, so you conjugate by some fixed element G, then clearly, because these translations are homeomorphisms on your group as a space, you get something that's also closed, okay? So you have this GH G inverse is also closed. Well, if it's closed, and clearly the identity is All right. So the idea is that if you're given a topological group that's potentially non-Hausdorff, then a lot of things get messed up together by your topology. Basically, you cannot differentiate two elements based on your topology. So if you just look at the identity element E, okay, and a lot of things get messed up, so you take its closure. That's kind of all the things that get messed up with by your topology. So it turns out that's going to be a normal subgroup of your topological group. And because you close it up, this is a closed normal subgroup. So when you take a quotient, well, from the last proposition, you know that first of all, when you take a quotient of normal subgroup, you get a topological group. And because it's closed, you know it's Hausdorff. Okay, so in this way, you kind of quotient out all these ambiguities of your topology, and you end up with a nice topological group that's Hausdorff. Okay. Right, so to prove this theorem is really just proving the closure of the identity, the singleton identity is a normal subgroup. Okay, so that's all we need to prove. Right, so from last lecture, from last video, we have the closure of a subgroup is also a subgroup. So one thing you know for sure is that the H is a subgroup. Okay, that's clear. Because you closed up something, when the identity itself is a subgroup. So close it up, you get a subgroup. And not only is a subgroup because you close it, always closed. Okay, so that's not surprising. So we just need to show it's normal. Okay, so if H is not normal, then what do it's not normal, then what we get is that there exists some element G inside G so that the conjugate is not equals to H. Okay, you conjugate something and you get something else. Okay, so that's non-normal. But one thing you know is that because your left and right translation are homeomorphism on the space, this topological space, your GHG inverse, you just translate some closed subset, you get something that's also closed. And also the identity is clearly a subset of this G inverse. Okay, so the identity is clearly inside there. Okay, in fact, GHG inverse itself is a subgroup. Okay, so what do you do then? Well, now you have something that's smaller than H. Okay, so you get something E is contained inside GHG inverse intersect H, but this is strictly smaller than the H. But your H is supposed to be the closure of the singleton E. Okay, so this is supposed to be the closure, the smallest closed subset containing this E. So, well, that's a contradiction. Okay, so there we have a contradiction. So we have all these GHG inverse has to be H. Okay, so H is normal. Okay, so that's the end of this corollary. Okay, so I just want to quickly remark a few things. So that's first of all, by this corollary, we always assume our group is Hausdorff. Okay, so we always assume Hausdorff in this course. The main reason is just because of this corollary. As long as you have something non-Hausdorff, you quotient it out. Okay. And when things are non-Hausdorff, it can get really weird. I don't want to get into any technical details, so let's assume everything is Hausdorff. And one thing we often talk about is that a locally compact group, that's the thing, the typical object we study. So a locally compact group, let's call it G, so is basically, by definition, is this topology is locally compact and is going to be Hausdorff, okay? So by whenever I say something that's locally compact, then I automatically mean is Hausdorff and locally compact. Sometimes a lot of the books assume this Hausdorff. Some books does not, okay? But in general, most books do assume this Hausdorffness. And even there's some convention even use the LCH, locally compact Hausdorff, to denote these locally compact groups. Okay, so sometimes I will say a group is LCH. What I mean is locally compact and Hausdorff.